What up, everybody? Welcome to a coffee hour. We have gotten to the end of the week. We have made it. We're on the downslide. The weekend's ahead. And it just seems like these things roll by as I guess it's getting older. It just seems like the weeks just keep clicking on by. The bones creak a little bit more. The fingers, the joints don't want to work. And it's just slowly creaking by. But we keep getting it on. I want to thank everybody out there for joining me here on Coffee Hour. It's Friday. It is the 21st of March, and we are ready to get our learning on. Today's episode, we're going to be talking about general requirements for conductors, just some top level stuff that all of you need to be aware of. And we'll cover some topics and just have a good discussion today, kind of lighten it up a little bit here for Friday, and we'll look at some requirements for conductors and ampacity and some of the rules that you just need to be aware of. That's what we're going to cover today. So got any questions on that, feel free to ask. Try to keep them germane to the topic. Other than that, I recommend you send questions through paulabernathy.com. And I don't deal a lot in hypothetical questions. That's code specific. If the code says you can do something, then I do it until an AHJ tells you otherwise. So those are the type of things that we cover in paulabernathy.com. So make sure you submit those. Also, if you've never been here before, my name is Paul Abernathy. I'm the CEO and president of Electrical Code Academy Incorporated. We are a Virginia corporation. We previously were a Texas corp. Now we are a Virginia corporation, and we've been in existence since as Electrical Code Academy since I believe it was 2007 or something, 2008, something like that. No, take that back, 2017. Prior to that, we're electrical service specialists, and we've been around for decades. And when we moved to Virginia, from Virginia to Texas, we just redid it and reincorporated in Texas, the same as we did here. But what we did differently this time is we kept the name. We changed the name when we went to Texas last time, but now we kept Electrical Code Academy Incorporated and got everything moved back to Virginia. So We had a company that did that for us, turnkey. Everything worked great. So everything's good to go. I do want to give a shout out to J&M Electric. J&M Electric up in Richmond, Virginia. I did a training session for them yesterday. Talked about wire and cable and went into some code changes and things because Virginia is on the 2020 edition of the NEC now. So it was good to meet with all his guys, and it was great. They provided lunch. It was awesome, and I enjoyed doing it. Jason and his wife Marcy own J&M Electric, and Jason's also a guy that I kind of was a mentor to years ago. He was successful. It's just we kind of connected when I was working as the engineer for the city of Richmond, and we connected in that relationship. He's a great young man, and he has really grown his business to doing millions of dollars worth of business a year. And so I'm so proud of him and happy that he's so successful. And his beautiful wife, Marcy, and it's got great guys, his two lead guys, Chris and Kevin that work for him. And that thing, they just do a great job. And I'm just, and Jason, excuse me, Jason and Chris. And Jason's son is now getting into the business, and so it's awesome to see that. So awesome to see a young electrical contractor succeed in a very busy market. So excited to see that happen. So congratulations to Jason, the J&M team. All of them did a great job, and hopefully they got something out of our training lesson yesterday. Okay, all right, so. As always, I live vicariously through you guys. So when you send something to us or let us know something about your successes, even your failures, because we can learn from failures and all those type of things, do me a favor, share them in the comments. And if it's the first time here, let me know your name, where you're from. If you're a regular, let me know your name, where you're from, what you got going on in the chat. And also don't forget to put #win to get in on our spin that we spin always towards the end of our show. So we can get you in on some drawings. We have quite a bit of people that are on these drawings, and we're going to be translating these over to drawings to be able to pick them out, that type of thing. So, also, we're not doing a behind the scenes today because I am actually streaming over on Instagram. And the more I thought about it, even though I'm boycotting TikTok, it didn't do any justice to the folks that like to watch over on Instagram, so they can actually see the lesson as well. So I figured, you know what? Very few people watch the behind the scenes anyway thing because it's just me. What's the point? So again, always changing. So that's what we've done. Okay, let's do some shout outs some morning. You know how I love to see all of our viewers and people that join us. Let's see here. We got Charlie's in the house. Good morning, Charlie. Thanks for joining us. We have Adam in the house. Good morning. Reaching out. Oh, hitting that beatbox Friday early. I don't know if I got the energy in me to do that. Charlie's setting the tone, the #win. So make sure that you hit that #win if you want to get in on the spin. You only have to do it once, but make sure you do it. What is up? Cray is in the house. It's the third best day of the week from Nashville. The third best day. Most people think Friday's the first best day. Okay. All right. David, what's up? Good morning. Happy Friday. Eric. Good morning. Welcome. Thanks for joining us this morning. David is in on the #win, so is Eric. We have our CMECP in the house from down in Florida. David, glad to have you here, my friend. And David also is throwing out that #win. There you go. Let's see here. Erie, thanks for joining us this morning. Glad to have you here on Coffee Hour. Terrence from right up here in Maryland, DC in Virginia area, right around my hometown. Terrence, I did get you set up over on Fast Tracks Tube, so go check it out. You are all set up. Christopher, thank you for joining, my friend. Glad to have you here. Tino's in the house. What is up? Good Friday to you as well. Let's see. Alex is in the house. Alex, good morning. Glad to have you here. Let's see here. We have Doug Webb. Doug Webb is getting in on that #win. Thanks for joining us. John, happy Friday. Thanks to have you here, John. Study. Dissect those questions. You got it. You got this. Jonathan, Welcome, Jonathan, down in Florence, Alabama. Beatbox Friday, man. Y'all like that beatbox? I'm not as good as I used to be. When I was younger, dude, I could hit a beatbox. Okay, I actually won awards doing that when I was younger. It seems like the voice in the mouth and all doesn't work as good when you get older. It's like everything is slower down. And maybe one of them feels sad in my face. I don't know what's happening, but it doesn't work as good as it used to be. I used to click very well. Dougie Fresh, that kind of thing. I am from that era. Okay, so hard to believe many people think I'm just an old fart, but dude. Red Dog, what's up? Glad to have you here. California in the house, student studying for that exam prep. Get on it, my friend. Glad to have you here. As always, you are a regular. I appreciate you coming. Kendra, welcome. Hearts back out at you too, Kendra. Thanks for joining us. Glad to have you here. Everybody hit that hashtag win. Edgar is in the house. Happy Friday. Glad to have you here, Edgar. I know that y'all can do a lot on your mornings, and I funny because I was just at J&M and Jason was like telling his guys, it's funny. He was telling his guys, he says, you'll have to watch the show at 8 a.m. And one of his guys yelled out, "Hey, that's fine, boss. You're paying us to watch his video for an hour. That's awesome." I was like, "Whoa, okay." So I get it. There's that take the time to do it. I'm probably doing it on your own time. But maybe you are supported from your boss that allows you to come to coffee hour. But either way, I appreciate having you here. What is up, Rob? Thanks for joining. You're on a mini vacation. All right, well, enjoy your time. Enjoy that little mini vacation. What's up, Haas? Richmond. I was just up in Richmond yesterday. Okay. I was actually coming back in the middle of our little storm that we got through Richmond. That was nasty. Let's see. Tina says, "You still got it. Come on, do it." I might do a beatbox before we finish today. That's something you got to hold on to. Okay. Good morning, Windy, New Jersey. Joseph, welcome over on Facebook. Dougie Fresh, he was the man in the day, buddy. Let's see here. Val, good morning, Michigan. Okay. Let's see. We got a bunch of hashtag wins going on. And then Paul wants us to make sure that we have coffee hours today, plural. More hours today. It's Friday, dude. When I'm doing a seminar, I always have to change during the seminars when I'm teaching these things, if I'm doing a live seminar somewhere, because I read the room and I always look for the younger guys. And if I'm looking for the younger guys and I see them kind of looking at their clock or watch and they start looking around, I realize they've either lost them or the topic's going over their head. You know that? So I'm always reading a room when I'm doing a seminar. Well, thank you. My wife is having a good day today. She seemed like she was sharp today, so that's always a blessing. Again, if anybody is living with anybody that's going through Alzheimer's or anything that's dementia, that type of thing, or age-related stuff, it's tough because you feel like that. I spent almost the better part of my life with her, because I got married at 18, 19 years old, somewhere in that age. So I've been with her my entire life. So it's not your partner anymore. It's your like your best friend. So when you see them slowly struggling with things, and it's tough, and it ain't gonna get better. I already know it. It's not gonna get better, and it's just one of those things that you got to deal with. Life throws you crap sometimes, and you gotta make a chia pet out of it, whatnot. So anyway, thank you all for joining me. And again, I appreciate you all coming here and taking time out of the day. Hopefully we can get your day started. Okay. So like I said, today what we're going to talk about, but before I get started into that, we want to look at a TikTok video. And again, apologize. It's probably going to be the double audio. I don't know how to fix it. Somebody that's more savvy than me, I don't know how to stop the audio, but I will point out the issues in it so that we can show you that I am, again, not sure. Look, I called somebody an idiot for making an improper statement, and I got a strike against me on TikTok. So I don't even know how long I'll still be on TikTok, because I've got so many strikes against me. I don't understand why I'm taunting them. I'm like, just delete me, because I can live without TikTok. But there's still so much stupid stuff over on TikTok and other social medias that people are propagating. Now, this video I'm getting ready to show you, you may have seen it. The guy has over 80,000 followers. Now, I understand that people follow stuff with the boobies jiggling and maybe that's just my feed, okay? I'm a guy after all, but I love my sandwich girl who makes the sandwiches. Can't help it. And no, I don't go, hey, I'm an old man. She's my daughter. Dude, she's 21. Hell, my wife's 20 years older than me, so get over that. So at the end of the day, I'm looking at age is just the thing, right? As long as you're legal. So at the end of the day, and I look at it and I go, how can people follow somebody that does that, that says things that are so wrong? And I guess they take them for what they are. You know what I'm saying? I'm going to assume that that's what they do. So I want to show you this video. And again, I am generally embarrassed for the gentleman. Okay. So this is the guy here, and it's called Redneck Logic versus NEC Rules. Now, the first thing you'll notice is this right here, and he shows it later. The first thing you'll notice, this is a remote distribution panel. Okay. And so he's running this, and he probably doesn't even have this strapped properly, but I can't tell. So anyway, he brings this down. First of all, now see, he's got a plastic bushing on this. That's okay, but it's not required because this is a cable assembly, right? But that's okay. You want to pay the extra $2-3 to put that little bushing on there, you know, that you go for it, right? But in this panel, this is also, he makes it clear this is a remote distribution panel. Okay, he makes it clear because he takes you to the panel outside. In this video, he's got the green screw right here. It is screwed all the way in, and it connects the neutral to the metal encasing downstream. This is a direct violation of 250.24b. Now, it used to be 250.24a5, but now in the 2023, it's B. And that tells you that you can't make an improper case to neutral connection or take the neutral and connect it to the metal parts downstream. It specifically tells you this, right? And the reason for that is that current's going to travel back to the source, okay? Current being some type of load, whatever, and everything's got impedance on it, so you'll have some kind of current flowing. If you take the neutral and you connect it to the metal enclosure and the equipment grounds downstream, then what happens is you get circulating current. You create objectionable current. You get current that can travel. Obviously, the majority of the current is going to travel back on the neutral because that's going to be a bigger conductor and it's going to have lower impedance. So again, it's all proportional, so it's going to travel that way. But you're also going to introduce current that can travel back on the equipment grounds, that can travel back on the metal enclosures and things like that. And the problem with that is if you happen to not, and I don't say that this gentleman torques anything like he should. I don't know. I'm not going to say anything bad about the guy, right? That type of thing. But what I will say is that we're notoriously in this industry don't torque properly. And if that neutral is not torqued properly, and this is aluminum, and you over torque it, then what happens is it'll loosen up over time. Even if it's 8000 series aluminum, you don't want to over tighten aluminum, okay? So what happens is that you create a gap in there. And then under conditions of loading over time, cycling, it can create a gap and an arc will take place, okay? Well, that's not even the biggest issue because I can't tell you whether he torqued or not. I don't know that stuff. Chances are, I'm sure he probably doesn't even know what a torquing screwdriver or wrench is. Okay, I'm just being real. Okay, I don't want to be nasty, but you know. But at the end of the day, it is a remote distribution panel. Now, whether or not he has that main breaker in there is irrelevant. Okay, because that at this point that's just a disconnect. I can tell you that you know right now that that's not a service because you see the SER coming in for Conductor. And again, it's going out and you can even see in the picture at the top of that picture, you can see where it is a bare and that is the equipment ground. So we know it's a remote distribution panel and we know what the code says. Okay, so we can go look at the code really quick in this because I just like to point out these things. And again, Evie Muck says it's my computer doing this, but it is impossible for it to be my computer. So I don't really care what they say. All right, so let's go to 250. just to show you where this is in the code. Okay, so we go to 250.24. We have the system grounding connections, okay? And we had all this A1, 2, 3, and 4, and it used to be at A5 right here, but now it is this. So this is called load side grounding connection. It says, a grounded conductor shall not, that's a mandatory rule, mandatory, it's not optional, it's not a permissive, it says it shall not be connected to normally non-current carrying metal parts of equipment, to equipment grounding conductors, or be reconnected to ground on the load side of the service disconnecting means, except as otherwise permitted in this article. Okay, article being otherwise permitted here in Article 250. Okay, so that's the general rule. Okay, and of course you have some information here that and again, you have a bunch of other things, and it talks about the parallel paths and what can happen, and we talked about it. Currently traveling back on that equipment ground, as well as the grounded conductor, in our case, a neutral, and it creates all kinds of problems, okay? Now, there are other areas in the code that may permit this application. This is why we cannot do a definition of objectionable current, because there may be other places in the code that would permit a similar application, right? But in general, it is not permitted, specifically prohibited, okay? So, good morning, gentle. Good morning, gentle peoples. I love that. Good morning, Dan. Thanks for joining. So, this gentleman is talking about it, and he's propagating it, and his panel is obviously incorrectly installed right from the get-go, okay? So, let's go on and go back to the gentleman. Here, let's see if I can get it back up. Okay, now I don't have any idea.
While it's common knowledge, most American building codes are designed to drive material.
Okay.
While it's common knowledge, most American building codes are designed to drive material purchases and increase workload, to increase the tax value of homes, to extract more money from homeowners and fees through re-inspections and contracting licenses and that from the population. Some of them just don't make plain fucking sense. Take, for example, the NEC rule that says you have to have your neutral and your ground separated in the main service panel at this wire.
Okay. All right. I'm sure y'all are getting double audio, I guess, and it's not sounding right. But you know what he's pointing? He's saying that he says that it's required to. Let me go back to it, because this guy. Hold on. I mean,
you have your neutral and your ground separated in the main service panel at this wire.
Okay. So first of all, the code doesn't say that they have to be separated at the main service panel. It says they have to be connected together at the main service panel. Okay, so he's wrong, obviously wrong there. And you folks can see the nifty little green screw that's right there. It is screwed in. And then you can see his equipment ground right here. So you know this is an SER. Okay. All right. So first of all, he's making the wrong statement anyway. All right. Okay. Now, we won't say anything about the fact that if this is a top plate, we don't see any fire blocking 300.21 in order to, maybe he's not done yet. Okay. And also these not having his cables secured within 12 inches, and no, they're going through here. So we won't get into, there's a lot of other stuff, that type of thing that's going on. But that's one of the things that go on. So this right here is a violation. Right, and we know this is a remote distribution panel. Now, again, I know the audio is echoing for you, but I'm going to keep it going so that we can see what else he says, so that you can actually see the outside panel, okay?
Wire, which then runs all the way over here, and right here to your meter main disconnect, where the...
Okay, so now this is the outside, and they are all connected together like they're supposed to be. Okay, that's what it says in the code. That's what it tells us in 250.24. Okay, so out here, he's correct. Okay, and he's actually using the adequate hole that would be for a GEC. Okay, you have no problem with that scenario right here. And again, you can see that he is dealing with an SER going in, and it's outside. Now, a couple things that I will tell you, just because I like to give you knowledge. All right, so y'all can hear me okay. See this right here? So this allows, I believe this is going to allow for some breakers to be installed right here. So by the way, if he put any breakers in here, then, and he was happened to use 310.12, which is the 83% rule, he could not use that rule on this sizing of conductor. Why? Because this conductor's feeding the panel inside is not seeing 100% of the load. He has some loads being breakers out here, and the rest of them being on the panel inside. That would make the use of 310.12 something you could not use on these conductors right here going in. Now, he could use it on the conductors that are coming down from the weatherhead, because those conductors would be seeing everything in this house. But these conductors would not be seeing everything in the house, okay? So just keep that in mind. You would not be able to use, if he was putting these breakers in here, you would not be able to use 310.12, the 83% rule on this right here. Just a little fact that I will point out, okay? All right. So at any rate, this video, this guy has over 80-some thousand followers. I have 12,000 followers, and I'm throwing up fact. This guy got 84,000 because, again, it's a classic example is that many people don't want to learn the truth on these social medias. They just like to see this kind of garbage that is misleading. It's false information. And it basically propagates improper installations. And I hate it. But yet I post something and I get a violation or a strike against me, right? These kind of people post misleading information like this, right? And I think he's even an electrical contractor, and this is what happens. So it's a shame that this is the kind of stuff that we get on social media. Okay. And so my message to you guys out there, especially the ones that are learning, anything that you see on social media, no matter what it is, whether I post it or whoever posts it, anybody posts it, always question it, take it with a grain of salt, do your own research, do your own due diligence, and really ask good questions, whether you use the trade hog or you reach out to me. Again, I don't get into hypotheticals, this type of thing. I try to keep things within the scope because I can't judge how an AHJ may interpret something. But the code is literally, so I have an email from a gentleman, he's probably on here, about fixture wire. And I gave him a code reference. It's designed for like pendants and things like that. But it's also designed for where you might make your own type of pendant, where you may come down off of a branch circuit and you might come down with a raceway to a stack luminaire or something like that. And so they give you an extended length of that fixture wire. But fixture wire, for example, is limited to the ampacity anyway, so you can only use it in very unique installations. So I couldn't give him a definitive answer on the longer lengths because it's a hypothetical. You have to work with your AHJ to see if they're okay. But if something says I can have 50 feet of fixture wire and I'm protecting it at its lower ampacity and I'm using it as fixture wire, then I ought to be able to use the maximum length that the code says. So that's just an example where we tried to give you the code, but again, sometimes it's going to be up to the interpretation, sadly, of your AHJ, and hopefully they look at something as a fixture wire and they treat it as a fixture wire, that type of thing, which is going to have a reduced ampacity value. So anyway, that's the best I can give you on that. So let's get into talking about conductors today. And it's just one of those things when you look at a video like that, you're just like, why would you even put a video like that out there? To me, it would just be embarrassing. And this is what I used to have the problem with Jay, is I had to stop really associating with it because some of the stuff that gets put out there, and I think it's just for clicks, I just can't deal with it. I'm a technical guy, and I know my stuff can be dry and boring and whatnot, and my videos are long and drawn out and all, but I just can't deal with the BS stuff. So I have to separate myself from a lot of those things because I am not about the clicky clicks, that type of thing. So every now and then I'll put a funny one up, but certainly not to try to get the clicks, that type of thing. So let's get to a lesson. All right, let's talk a little bit, see what we can get through in a lesson today. We're going to be talking about Just some electrical wiring. We're going to talk about the general requirements of conductors, okay? That type of things. And I hope Adam's right. I hope every electrical inspector out there would fail that installation we just looked at. If you're an electrical inspector out there and you pass that guy's installation, you need to go back to plumbing. I'm just saying. I'm just saying. All right. So what's our objectives today? If we can get through this today, I'm going to try to keep you to an hour. We're going to explain important factors that are considered about conductors, talk about conductors a little bit. Actually, it's one of the things I do all the time. Okay. And so we're going to be talking about that, looking at ampacities, looking at conditions of use, kind of giving you an example of conditions of use that you guys may run into. If you have any questions about conductors and application and use and recommendations and all that stuff, this is a great episode to ask those questions. Which conductor we recommend for direct burial and for raceways underground? Is it okay for THHN, THWN? Anything that you want, feel free to ask. Ampacity, continuous versus non-continuous applications, feel free to ask them. I'm more than happy to try to answer some of those little burning questions that you may have had. Okay, we'll look at some installation types. We'll even look at the NEC because there are some great tables in the NEC that we need to look at. We'll explain some of the applications and the multi-ratings of some conductors, different ampacities, dry, wet, damp. And we'll talk a little bit about adjustments and corrections using 310.15b11, 310.15c1, a little bit of that. Again, we'll talk about neutral conductors and which ones are considered current carrying or not. Just kind of general summary, and we'll just kind of cover again. I'll give you the voltage drop formula for what it's worth. You probably have already watched our voltage drop videos, so you're probably okay with all of that anyway. So it's kind of our summary of what we're going to talk about. Now, some of the things to think about as an electrician, as you're doing this every day, not blindly. I mean, you're an electrician out there, even if you're doing work on a drawing in a commercial and you're just following what's on the drawings. One of the passions that you should have in our trade, because other than that, you become a robot and it becomes very boring. You should have a passion to say, well, why do we do what we do? And I want to learn the reasons why we do what we do. And that doesn't just make you a better electrician, right? What's up, Manny? Thanks for joining us. Glad to have you here. That type of thing. Is that you want to make sure that I know the why behind everything that we do. And if not, it makes you have to ask these kind of questions. Okay, so every portion of electrical installation that we're going to do is going to have something that may affect its use. We call that a condition of use. Whether we're running cables or individual conductors in raceway through a boiler room, or we're running it on a rooftop, and we have some situations where a condition of use is where the elevated ambient temperature in the area where I am running it is going to be raise the ampacity, reduce the amount of ampacity a conductor can carry due to the elevated ambient temperature. So ampacities that we use every day in the code are found in table 310.16. So that's our general ampacity table. You all are familiar with that. And if you're back in the older code, it was 310.15 B16. But now it's 310.16, okay? And when you think about ampacity, that is ampacity of that table. That is the ampacity based on a condition of use that is 86 degrees, 30 degrees Celsius, 86 degrees Fahrenheit. Perfect. Now, we don't live in a perfect world. But if you're running through conditioned space, you're running through in the walls inside of the building, then it's going to be where the building is going to be conditioned. Then we don't take any of that. We don't care about most of that stuff. We don't worry about ambient temperatures when we're running it in walls and stuff like that. We don't typically worry about that. What we do worry about is how many current carrying conductors we have, how many cables we have. Are they in contact with thermal insulation? Are they going through bored holes that are thermally packed? All those type of things. Are we bundling cables without maintaining spacing for over 24 inches? All these type of things. Are we taking a raceway and we're just dumping conductors into it and we're not taking into consideration the fact that there's mutual heating, and how do we get rid of this heat? So all those type of things can change what we call the condition of use. Right? Now, when that happens, then we have to change the ampacity of a conductor. So when you think about the ampacity in 310.16, if world is perfect, 30 degrees Celsius, 86 degrees Fahrenheit. If it's perfect, then we can pull the ampacity directly from that table, depending on our terminal limitations, 60, 75, or 90. We're good to go. Reality in the real world is it's never perfect. Now, I know as well as you, and guys, don't lie to me now. You know, we're in a truth zone here. We're in the middle of a truth zone. When you're installing SE cables or you're installing conductors going from the outside to the inside from your panel or maybe even your emergency disconnect for 1 and 2 family dwellings and you're running them in, do you really even think about the ambient temperature that's outside? Probably not. I can promise you that you guys probably don't look at it and go, from this meter to this exterior emergency disconnect, or it could be your main disconnect and service both, whatever. Could it get hotter than 86 degrees Fahrenheit? Probably. If you're down in the South, you're in Alabama, you know damn well it's going to be hotter than 86 degrees Fahrenheit in the middle of the summer. But do you really do an ambient? Do you take advantage? Do you do anything with it? Do you make a correction for it? Okay. Chances are you don't. And it works fine. The good news is because the insulation on today's products are very, very forgiving. So you can have some temperature swings. And so remember, even if we're limiting things to 75 degree because of terminals or even 60, remember that in most cases today, the insulation on our conductors are probably going to be rated 90. Now, we can use that 90 for adjustment and corrective purposes, but at the end of the day, it's still rated 90, okay? So 194 degrees Fahrenheit, that type of thing. So there is a bit of a cushion factor that's built in that the wiring cable. Now, I'm going to tell you as a wiring cable guy that the insulations that we make today are much better than they've been made years ago, much better catalysts, much better. So again, the code didn't change. The rules didn't change, but the insulation got better. And the reason for that is going to actually give you an even better cushion down the road. If you have a situation where the ambient creeps up, you're at least going to be a little safer. You're not going to have conductor breakdown, that type of thing. So again, insulations, manufacturers, Southwire, Prismium, Encore Wire, Cero, CME, all those companies, all have gotten better at making insulations for our conductors over the years. Again, constantly R&D development, trying to make it better catalysts, better compounds, better pelletized material, all those type of things. Okay, so anyway, all right. So that's what we're talking about. Now, our job as engineers, electricians, is to design or install electrical systems, and we have to make sure that we choose the proper conductors. We have to make sure we know that what we're terminating on load. So we're the reason we get the big bucks, right? Electricians, we got to do a little more than just gluing two pieces of pipe together and putting water pressure behind it. We have to do a little more, and that's no disrespect to the plumber. I'm just saying what we do kills people, okay? We have a question. Jonathan asked the question, says, what is conductors made for with higher than 90? Well, you have applications where you have other tables in the code, which 310.17, we have that, which is typically 90, but then you have 310.20, 310.21. So you have higher insulation temperature ratings for higher voltage classes. You'll have a higher temperature rating for medium cables, medium voltage type cables. So you'll have a higher, generally when it comes to building wiring, okay? And you also have a higher voltage rating for some applications for when you're dealing with something like machine tool wire, maybe, not usually not, but appliance wire that's going into appliance could have a varying different insulation. So it depends on the use. But for building wire, we typically don't go over 90, okay? And again, could I use the 90 ampacity under the 90-degree column? Could I use it? Yeah. If my lugs are rated 90 and my conductor rated 90, right, and my terminations at the end load are rated 90, then nothing says I can't use the 90, okay? But usually we're limited, okay? So usually there's something that's going to hold us back. That might be the breaker's limitations at its terminals. It might be the lugs limitation in the equipment, things like that. So usually there's something that's limiting us because, again, the higher the current, the more amps that can be drawn, okay, and that type of thing. Okay. Well, let's see here. Yeah. Let's see. What is Angel? I'm sorry, Angel. What did you say here? Thanks. I won faster yesterday and I signed in. Thank you for your work on the elections. You want to learn? There you go. Well, glad you got all hooked up and we got you all squared away. Hopefully we did get you upgraded if you won that yesterday so that you get access to it. If not, let us know. We'll get you upgraded. But it sounds like you got upgraded, so it's good. All right, so we're going to kind of look at some stuff here. This is a lot of stuff, so buckle up because we're just going to go through this very quickly. But one of the things I will tell you is when you as an electrician start thinking about a circuit, you need to think about the circuit as a three-pronged approach, the pitchfork approach. You have the breaker or lugs at a breaker or lugs at the overcurrent device limitations you have to be aware of. You have the span of the conductor, where it's running from point A to point B, which could have a lot of conditions that take place in that long span, whether you're running at 20 feet, 15 feet. And then you have to think of the end, where it's terminating, okay? So if the lugs on a breaker are typically they're going to be 60/75, and most of the wire we use today is going to be at least 75. So that's why we get away with using 75, except for like a non-metallic sheath cable, which it limits you to the 60. But it does allow you to use a 90 for adjustment and corrective purposes only. But my point is you may be limited at the breaker. You might be using an insulation that is higher than whatever the breaker rating is. But then you get to the other end and the lugs or the terminations onto the equipment may drop it back down to 60, let's say. So you have to understand every piece of the installation. And I think today a lot of times we take all of this for granted and assume everything is rated 75 or even 90. So we have to be very careful in our terminations. Now, if you're a service electrician and you do a lot of service work, then you're probably going to go onto some service calls where you have no freaking idea what the lug's rated for. It's just old. And you have no idea. Maybe you can't even see the markings on the insulation, that type of thing. Well, if that's the case, then you're going to have to default to 110.14C1, for example. So if it's 100 amps or less, okay, or 14 through 1 gauge, you're going to default to the 60-degree ampacity column because you don't know enough information to not do that. If you get there and you find a lug that's rated 75 and you can't determine the marking or what the insulation type is on the wire, you can't see anything, and you don't know or you know the lug is rated 75, right? But you don't know what the insulation rating is of the wire. You just have no clue what it is. Then guess what? If it's 100 amps or less or 14 through 1, you're going to be stuck in the 60-degree ampacity column of table 31016. There's nothing you can do about it until you know what type of insulation it is. And so there is, sadly, a lot of insulation where you may come in and want to put a new breaker in, and you're using existing wiring, and you're putting in a new load, maybe something at the end, and you know what those ratings are, but you have no idea what the wire's rating is, okay? Then if that's the case, you have to default. Now, if you're in the lucky position that you determine that the wire is larger than 1 gauge, okay, so 1 aught and larger, then you can automatically assume that you're dealing with a 75-degree C and you can go about your merry way because of the size requirements. But if it is 1 and smaller and you can't identify anything, then you're stuck with this weak link, we call it. So remember, key takeaway today is that any circuit, right, is 3 different applications, okay? It's the termination, it's the span, and then it's the load. 3 different things that you need to consider. And again, the variables can change all through that installation, okay? All right, so what is ampacity? And ampacity is defined in Article 100 as the maximum current in amperes that a conductor can carry continuously under the conditions used without exceeding its temperature rating. Did you guys know that 310.16's ampacity? Did you know that is actually that the amps is considered continuous loading? So the amps that I see in 310.16 is actually continuous load. So whatever I see in 310.16 ampacity, it could pull that that ampacity forever, and not melt down that insulation. Yeah, it can pull it that. So every ampacity that you see in 31016 is based on it's a continuous maximum current it can pull, okay, forever and never break down that insulation. Now, the problem is in the National Electrical Code, the code says, yeah, I get that, but we're going to tell you if something as far as protecting the wire, it's going to tell you that if you're pulling a continuous load, and what is a continuous load? Something that's pulling its maximum current continuously for 3 hours or more at its maximum, not partial, not if it's thermostatically controlled and it cuts off for a little. That's why your range, if I'm cooking a turkey on Thanksgiving and it's in there for 3.5, 4 hours, that's not a continuous load, okay? Because it's thermostatically controlled. It'll never be pulling the maximum output, okay? That's just an example. But lighting, for example, in a parking lot that's going to run all night long, or lighting in a commercial building that is on all day, that is considered continuous loads because it's pulling its maximum output. And it doesn't even matter if you could dim that back. If you can turn it back, it doesn't matter because it has the ability to be at its max, so you're sizing it to the max, that type of thing, right? So if it's a 100-watt lamp, then it has a maximum of 100 watts. When it's on, it's on. The fact that you dim it back is irrelevant. It has the ability to be on continuously at 100 watts. So we treat commercial lighting, parking lot lighting, all of that kind of stuff as a continuous load. Right? So, but nothing in a dwelling we can treat as a continuous load except for where it tells us to treat it as a continuous load. For example, if we're doing a water heater and we're installing a branch circuit to a water heater, and a water heater is a 120 gallons or less storage type water heater, then what does it tell us in 422.13? It says size those branch circuits at 125%, okay? Well, chances are that load could be on for 3 hours or more at its maximum output, but again, it doesn't matter because the code tells me to take it as a what? 125%. So that's another important thing for you to realize, that the code is going to tell you it, even though it may not sound like it's a continuous load, by the definition, the NEC will tell you as such, and you treat it as such. Same thing for branch circuits to EVSEs. So 625 will tell you to treat it as a continuous load, okay? Or it'll tell you to treat it at 125%. Those things, so you just do it, and you don't question it, that type of scenario, okay? All right, continuous versus non-continuous current, we just kind of talked about that. Ampacities in 31016 determine a conductor's ampacity, and we deviate from that depending on the conditions of use. Again, that table, 31016, y'all should all be familiar with, ampacity table. That is based on 30 degrees Celsius, 86 degrees Fahrenheit. And also, it is based on a situation where you don't have more than 3 current-carrying conductors. So, that ampacity table, if you have an ambient temperature that deviates from 30 degrees Celsius, 86 degrees Fahrenheit, you're going to have to make an ambient temperature correction. If you have more than 3 current-carrying conductors, you're going to have to make an adjustment to that ampacity that's given to you in that base table, okay? So again, if the insulation varies from these conditions, and this is your condition, all of this is your condition of use, right here, for that table. Any deviation, you got more than 3 current-carrying conductors, or that ambient temperature correction is what? Higher than the ambient temperature, higher than this right here. And if you have both, you're going to have to apply both. If any one of those are the case, you're going to have to apply one of those, okay? And like I said, there's a high probability that even when your service conductors that are outside, there's a high probability that you don't pay attention to the ambient temperature. Now, that does not mean that I want you to go out and start doing that, okay? I'm just saying there's a probability in the real world that you sometimes, for even everybody that says, I do everything per code, now there's a high probability that you really don't. But again, we don't see things burning up and that type of thing. It's when the obvious takes place, when we're running raceways outside, that the inspectors key in on this, when we're putting, an ambient temperature, or when we're running on rooftops, or we're running on the side of a building, and we know that the ambient temperature is going to affect the ampacity of those conductors, then we know we have a problem. Okay, so that's when they usually see it. All right. Let's see here. For installation of conductors in raceways, cables are directly buried. It's important to understand and choose the right conductor, the right installation type. Absolutely. Not all conductors are wet location rated, that type of things. But many of the products we use today are dual or triple rated. We'll kind of give you an example of that. The ampacity values or temperature ratings that are on the table, 31016, are 60, 75, and 90. And you can see the equivalent Fahrenheit for that. Obviously, the more conductors you have, the more current flows, the more heat's going to be generated. Okay, so I times R squared, R being the resistance squared, times I being the current, is going to give you what the wattage is. Obviously, the more current, the more heat. Obviously, that's a no-brainer. Okay, the resistance of a conductor depends on the size. That's a no-brainer too. Y'all know if you go to Chapter 9, Table 8, and you look at the resistance, you can actually see as the conductors get bigger, then the resistance gets smaller. As the conductors get smaller, the resistance gets higher. It's basically the resistance or impedance to current flow. It's restricting its flow, kind of like how water flows through a water pipe, that type of scenario. We want to get more current. We want the flow. Then we get bigger wire. Then we reduce the impedance of the current flow. And that's how we can get more current, and obviously makes sense out of a larger conductor. Okay? And of course, all resistance values, Chapter 9, Table 8, but there are resistance values as well in Chapter 9, Table 9. If you're doing a unique situation of a three-phase application using RHH or RHW-2 wire, then that table is typically what you would use for that three-phase application. But most of the time, we can get away with using the DC values. Why? Because AC versus DC, current in a DC circuit flows throughout the entire conductor, whereas in AC, it tends to migrate towards the outer perimeter. We call that the skin effect. But in 60 hertz systems like what you and I mainly deal with, the skin effect is very minimal. So it's usually negligible in how we would calculate it. Not the same if we're doing medium voltage and we're starting getting something with a much higher frequency, then that skin effect can be something that we have to take into consideration. But building wire, like what me and you do and that type of thing, negligible in that. Notice that the temperature rise, how it can change very quickly depending on the amps that you put. So a 25% load change on a circuit, go from a 16 amp draw to a 20 amp draw, they result in a 50. Again, this is basically using that I squared, I times R squared concept. Then what happens is you will see that the actual heat will change quickly. So from 16 to 20 result in a 56% change in the heat. So it adds up very quickly. Good news is our insulation is very robust today. So it can, again, handles a lot of those changes very well. But have y'all ever heard of a scenario? Have y'all ever heard of a scenario where you have this thing called plasticizer dripping, or this clear liquid that's dripping out of a thermoplastic type of insulation? That would be like a THHN, THWN-2, those type of things. Have you ever heard of that happening? That clear liquid that drips out of it? That's called plasticizer. That is put into a thermoplastic insulation or to give it pliability and flexibility, and it adds to the overall durability. The problem with it is that if you overload a circuit and you put too much current, in other words, you didn't size a circuit properly, then what happens is that it causes that insulation to heat up to the point where it starts oozing out that plasticizer material. What that means is that it's weakening the integrity of your insulation, and over time it will become brittle. Now, does that mean it's an imminent failure? No. It just means that you are lessening the reliability of the long-term use of a thermoplastic product because you did not take into account what? The ampacity and loading properly. And that's usually the engineers that don't do that right. I've been involved in quite a few cases where the engineers did not take certain loading. Usually it's database, and they didn't account for future loading, and now they're pulling way too much more current through a conductor than it was intended originally, and you start to have this plasticizer migration, and it comes out of the end where your breakers are, and it migrates, okay? And it migrates to the heat, okay? So it's gonna move viscously towards the termination, things like that. So we see that, and that's usually because somebody didn't take into consideration how they size their conductors, or they didn't torque properly and you have an excessive amount of load, of arcing load that's happening at the termination. So check your terminations, do a load calc, check an amp probe, see what you're drawing, but that's what you'll see. You'll see some of that clear liquid, and that's not nylon, by the way, on those products. That would be plasticizer, that type of thing. And again, just things to think about. Okay, so thermoplastic installations, probably the most common that you're used. That's what you're going to see in THHN, THWN-2, THWN general, THW, THW, all these type of, this is all thermoplastic. The material that you see in your non-metallic sheath cable, as many refer to it as, say, a Romex, which is a trade name of Southwire. That product, the insulation that's inside of it is equivalent to THHN, okay? So we all know that non-metallic sheath cable cannot be installed in a damp or wet location, okay? We get that in 334.10 and .12 where the use is permitted, and .12 is use is not permitted. It'll tell us not to be used in a damp location, wet location. You use UFB for that, okay? And you can use UFB inside of a building as well and use it like NM in those situations where you may need to transition from a dry location into a wet location. You can do that. There's no problem with that. But the inner conductors in a non-metallic sheath cable are equivalent to THHN, or they're equivalent to TW. More often than not, it's going to be equivalent to THHN. The only difference is we're not going to put marking on it because the standard allows us to put marking on the cable's jacket rather than on the conductors. And believe it or not, when you're a company and you're producing millions and millions and millions of feet of wire, if you can save without putting the ink on it, you can literally save over $100,000 or more a year alone. And you know what? Every dollar counts when you're, publicly traded and you're going to the shareholders. So, and again, it doesn't make sense to put that marking on it when the standard allows me to put it on the sheathing. So that's what most all of us manufacturers do. So that's another reason why you can't take an NM cable and strip out the inners and use them in a raceway, just the inners, because they don't have the markings on it. And so we're also required in the code to have all these marking requirements. And without those marking requirements, okay, no inspector or anybody can see what's being utilized, that type of scenario, okay? All right, so anyway, that's good. So that's called thermoplastic in scenario, and there you go. Now, the other most popular, in my favorite, is obviously the thermoset, okay? And the thermoset differs from thermoplastic in that think of thermoset is like a birthday cake, whereas think of thermoplastic like a Hershey bar. If I raise the heat on a Hershey bar, it's going to melt into any form we want, right? So even though both of these products, thermoset or thermoplastics, are rated 90 degrees, 75 degrees, 60 degrees, even though they have the same temperature ratings, they're still much more resilient in a thermoset because if you think of a thermoplastic as a Hershey bar, it gets really hot, it melts, okay? And that's what happens to the plastic. If it gets really hot, it melts. That's why we have to change the ampacity that we're putting on a conductor because we're trying to keep the ampacity and the heat from getting to the volatile point that the insulation melts. So that's really what we're doing, guys. When we're doing these adjustments and corrections, we're trying to lower the amount of current that we're going to be putting on it, or we're increasing the conductor to compensate. We're trying to adjust for it because we don't want to damage the insulation, which is basically keeping you from having short circuits and ground faults, okay? Or become a hazard touch issue, right? So the difference between the thermoset, and I said treat it like a birthday cake, is because when we make thermoset, it's basically what's called a cross-linking polymer process. Whereas the strands of a thermoplastic run parallel and they can be melted. Whereas a thermoset, they interlock and they act rigidly stronger. So it's a much more durable insulation from damage and scuffs and things like that. But it also has a much better thermal property, means that it can be used in lower temperature values as well as higher temperature values. But for me and you, we have to remember, as far as ampacity goes, 90, 75, and 60, the insulation still has to follow those 90 degrees, 75 degrees, right? But its exposure to temperatures is better, right? So, for example, the typical thermoset type of things where we mix all these chemicals together, all these catalysts together, there's no plasticizer in this. We mix all these chemicals together, and then we heat cure it, or chemical cure it, and it creates these interlocked molecules, and it becomes strong. So heat will not make it melt. Now, it can get so hot that it will crystallize and damage, obviously, but it will not melt. So that means it's much more resilient in areas where you may have an elevated ambient temperature. It also means that thermoset is a much better choice, for example, in raceways underground, because thermoplastic, everything has porability to it. So even though THHN/THWN-2, the THWN-2 can be used in raceways underground, if it's going to be a flooded raceway, and most raceways will be flooded, I recommend you use a thermoset rather than a thermoplastic, because it's going to be much more resilient over the long term. Now, does that mean you can't use a THHN/THWN-2 conductor in a raceway underground? Absolutely, you can use it. I mean, the code says you can use it. It's listed for wet location. Raceways underground or wet locations, you're perfectly fine. I'm just giving you advice long term, knowing that those raceways are definitely going to be saturated. Thermoset is a step up in that reliability, but both are acceptable. I just want to point that out. That's an opinion, but it is fact in the sense that thermoset is designed to be more robust. Now, also, here's some examples of thermoset. RHH, RHW-2. Used to be rubber in the day, but now it's chemically equivalent, so that's why we call it RHH, RHW, and it's also available in RHW-2. XHH, XHW, all of these not very much used. So again, not a wide use type of product, that type of thing. But you're going to see a lot of RHA. And then the other one is XHHW is probably the most, this one is the one that's not widely used. XHHW is probably the most widely used. But did you know that PV wire is also thermoset? Now, it can be PVC as well, a thermoplastic, but majority of the PV wire that the industry sells for the robustness and knowing it's going to be exposed to certain things, it usually is going to be a thermoset type of insulation, okay? Another difference that you can tell is typically these thermoset products, there's no extruded nylon over it. That is something that's reserved for thermoplastic like THHN. The N means nylon, that type of thing. Typically, what you have in a thermoset is just a straight extrusion. It's a solid conductor, okay? That type of thing. Solid insulation, okay? Obviously, conductors are available in copper, aluminum, and this other type of material. Copper wire obviously is the most common used, and again, it's still the king. It has the lower resistance, obviously, than aluminum, that type of thing. But again, aluminum is a good alternative, that type of thing. One day I'm going to do a class on here, and I'll explain the differences in the copper and aluminum and where you may be beneficial to use aluminum versus copper, even though copper is king, that type of thing. Now, some conductors insulation do have dual use. For example, like you see right here. So this is not as common anymore to just see THWN. Usually there's going to be a -2 beside it. And that -2 means that if you just were to have THWN, then you would have thermoplastic, heat, wet location with a nylon covering. But since it only has one H, it would only be 75 degrees is the temperature rating of that insulation. So whereas here you see thermoplastic 2 H's. So that would be 90 degree, 2 H's. So no H 60, 1 H 75, 2 H's 90. And you see there's a nylon covering. This is a dry and damp location product, right? Believe it or not, did you know that? THHN is a damp location okay product, right? And if it's a wet location, then you would use the THWN portion of this wire insulation. That's called a dual rated product. Now, the -2, so without the -2, even if I ran it in a raceway in a wet location, and I had to do an adjustment or correction, remember what we said we can use a 90 for adjustment and corrections? I would not be able to do that. If it's in a wet location in a raceway underground, I could not, if I was the engineer, I could not adjust from 90 because this insulation in the wet location where we're choosing to use it is only rated 75. So I'd have to do my adjustment or correction from the 75. That can screw you. in doing this adjustment, because you could end up with a conductor that won't have ampacity to do the load that you need. So this is why most all of our manufacturers use the -2 rule. So it'll say THWN -2. That -2, and look at some wire the next time you look at it. That -2 is telling you, hey, that -2 is basically replicating two H's. So it's basically THHWN when you see that -2. So what that means is I can use the 90 degree for adjustment and corrective purposes. I can use the 90 degree ampacity to apply my adjustment and corrections. Now, I still can't exceed the 75 or the 60, depending on what my other limitations are, but I can do the math from a higher ampacity and see if I still have a conductor after I do the math to handle the load that's in question, okay? So if I had a conductor that's worth 30, okay, and I have a 12, and for example, a 12 gauge is good under the 90 for 30 amps, but I know that it's limited to 20. So if I go and apply an adjustment or correction to that 30, and after that, let's say I have a conductor that's worth 21 amps, because I'm using it from the 30, does it still have enough ampacity under the 75 degree column to handle the 20 amps? Absolutely it does. It's good for 21. Now, it doesn't mean I can use the 21 because of the small conductor rules, but what it means is I still have a conductor that has enough ampacity to handle the load, even after I did an adjustment and correction from the highest ampacity. That's why we do this. And so we just want to make sure we have a conductor that can still handle what? Our load in question, and two, not going to exceed the ampacity values based on our terminal limitations, okay? And that was the 60 and the 75, that type of thing. Okay? So that's why we really do all this. We want to protect the conductor, okay? We don't care about the equipment, although that's a byproduct. We want to protect our conductor, okay? Now, why do we do continuous loads? If we told you that the ampacity of a conductor in that table is continuous, why do we apply 125% to continuous loads? For example, branch circuits 210.19. Why do we do this? It's for the breaker, because the traditional standard breaker is limited to 80%, okay? So the reciprocal of 80 is 120, okay? So if I have a 20 amp breaker and I want to limit it to 80%, then I take the 20 amp breaker and I multiply that. That's like 20 times 0.80, and that is 16 amps. If I know the ampacity of the load and it's a 16 amp continuous load, then I can use the reciprocal. I go 16 times 1.25, and that's 20 amps. So when we're doing things like looking at ratings of breakers and wire, and we have to treat something as continuous load, we just need to know which one we're working at. If I have a 20 amp breaker and I want to know how much continuous load I can put on it, then I take that 20 amp breaker and I multiply it by 80%, it tells me 16 amps. If I have a 16 amps continuous load and I have to size the conductor because they tell me to, or it's a continuous load, then I size that conductor, that 16 amps, I do it at 125%, right? And I size the conductor. That type of scenario, because that's a condition of use that I'm being forced into, is for a continuous load, okay? And then I go up and look at it and go, well, what about that breaker? All right, well, 210.20 says take that continuous load, which is the actual load, do it at 125%, and my breaker can't be less than that. So there you go. So it's just a process. It's an exercise. I encourage you to go watch my video on derating demystified. It is available over on Fast Tracks Tube, and you'd be amazed what you're going to get out of that in these little processes, that type of thing. All right, so one of the tables that you need to get really familiar with is 310.4. And this is a great table because it kind of correlates for all those questions that people have about conductors and all. And I want to take you there. And let's see, obviously it's got to do my little trick here. We're going to go to look at this table. And it's going to be a table that many people don't think about. And it used to be 310.104, by the way. But here it is. I'll just kind of blow this thing out. Let's see if it'll let me expanded view. So this is what we're looking at. This is, to me, is an amazing table in the code because this gives you the rundown of the general products that you're going to use in building wiring. All right, so we'll just go down and I'll show you because you heard me talk about the ratings of THHN and THWN-2 and all this kind of stuff. So let's kind of go down And so here's THHN. Okay, so this is a heat-resistant thermoplastic. You see that it's rated 90 degrees. Okay, that's the insulation rating. Dry and damp locations, you heard me say it. These are the normal sizes over here that it comes in. Okay, all right. And then you come down and you say, well, what about that THWN? Well, there's your THWN right here. If I did not have that -2 on it, then it would be 75. Okay, now obviously I can use it in a dry and wet because, again, the wet is a more restrictive use, so obviously I can use it in dry. The only problem is if it wasn't dual rated, then I would be stuck at 75. But since it's also rated THHN in a dry location or damp, I can use the 90. In a wet location, if this is all I had the markings, then I'd be limited to 75. That's a dry and wet location. Now, why again is that important? Well, if I have a situation again where I'm putting a conductor in a wet location, and I've got a bunch of current carrying conductors in there, and I now want to do a correction, or excuse me, an adjustment for the number of current carrying conductors, I can't start from the 90, can I? I can't start my math from the higher ampacity. That's such a benefit to us or to engineers. I can't do it because that insulation is not rated for 90. It's rated for 75, right? So what happens if I go down here and it's THWN-2, then you see that all of a sudden it's now rated 90. Same use, but it's now rated 90. That's so important about that -2. Okay? And there are products out there that you can still get today that are like in things that they call coil packs or whatnot. And you have to be careful because, for example, at Encore Wire Prismium, all of our THHN is dual rated and all of our THWN is always -2. Okay? I'm not plugging a company. I'm just saying, if you're doing circuits and the engineers thought that it was THHN, THWN-2, not all manufacturers will put the -2 on all of their small 14, 12, and 10s. So that could screw you at the end of the day if you need to make an adjustment or correction. And that could screw you because a savvy inspector may come out there and look at it and go, whoa, home slick. You did all this from the 90, but that insulation's THWN in this wet location. I'm not going to let you do it from the 90. You're going to have to adjust it from the 75. And what's the problem with that? Well, now you may have a conductor that after you apply the adjustment, it doesn't have enough ability to carry the current that you need to handle the load, where it would have been okay if you had to start it from the 90, but you had to start from the 75. So you just got screwed because somebody didn't pay attention to the markings on the wire, that type of thing. Okay, so that's just things to think about. But that is a great table because it goes over the ratings and the temperature ratings. And again, it's just one of those ones that you go back and look and allows you to see what you've got going on. Okay, now, anytime that we have a situation where we've got a temperature, wherever we're installing our raceways or our cables, anywhere that we have a temperature that we know is going to deviate from 86 degrees Fahrenheit or 30 degrees Celsius, whether you're running it in an attic or whether you're running it outside in raceways, however you're running it, if there's going to be a situation where you know the ambient is going to deviate from the ampacities in 31016, okay, so those are given, right? You're going to have to do what? You're going to have to make a temperature correction. And where do you go for that? You're going to use 310.15b to do that. Okay, so if we go look at the code and we go back to it, we're just going to go down and look at it really quick. 310.15, and we're going to go down and we're looking at B. So here is where you'll be doing your ambient corrections. Okay, all right. So here is for rooftop. So if I'm installing raceways, okay, and I'm installing conductors in a raceway, and I'm installing them on a rooftop, okay, if I'm installing it in the bottom of my raceway or my cable, okay, because could be installing a PVC jacketed MC or something up there, if it is less than 3/4 of an inch from the surface of the roof to the bottom of my raceway or cable, if that area is less than 3/4 of an inch, then I have to add an additional 33 degrees C adder or 6 degrees Fahrenheit, depending on which one you're using. So how do we do that? So if I'm on a rooftop and I've determined, and I'm using ASHRAE or Copper Development has a nice rule to tell you what the ambient temperature to use in your area. You can go to find out what the average is over a year in your area and use that as your baseline. Your jurisdiction may provide that for you. Whatever it may be, if you're installing a raceway on a rooftop and you are from the rooftop to the bottom of your raceway or cable is less than 3/4 of an inch, then you're going to have to take whatever that ambient temperature was. Let's say that the average ambient temperature for your location in your state, let's say that it is 92 degrees. I'm just throwing a number. Then if you install it and you like lay it on the roof, for example, basically what you're doing, okay? Then what happens is I have to take that 92 and I have to add an additional 33 degrees Celsius to it. Now, if that's 92 degrees Fahrenheit, then I have to add an additional 60 degrees Fahrenheit to this. And then I use that to do my calculation using the table in 310.15b1, okay? So that's called an adder. Now, here's the great thing about using something like XHHW, which is a thermal set. If you put thermal set XHHW, and it only applies to XHHW, I don't know why it wouldn't apply to RHH or HW-2 or whatever, but the code only says XHHW. So you have an exception. So anytime you're running it on a rooftop, you want to use X inners, and that means you can ignore this adder. Now, you can't ignore the no ambient temperature that you have to do anyway for whatever it may be. If it deviates from what? 86 degrees Fahrenheit, 30 degrees Celsius, you still got to do this this correction for the temperature, but you don't have to worry about the adder if you use XHHW-2 inners in it. And that's a testament to the fact that thermoset products can handle heat much better than a thermoplastic product. So always make sure that you're using XHHW if you're going to put it in a rooftop, and then nobody can question you by having the adder, or at least make sure that they're always above 3/4 of an inch from the surface. That type of thing, and then it doesn't really matter, that type of scenario. Make sense? Okay, but the key thing here is you do have this ambient temperature that you have to be aware of, and you're going to have to make a correction for that because it can affect the amount of ampacity that conductor can carry before it reaches that volatile threshold and your insulation starts melting down. That's why we do what we do, okay? All right, so the next one is, okay, well, what if I have a raceway that's got more than 3 current carrying conductors in it? All right, well, then there we're going to have to deal with table 310.15c1. Okay, so that is the table we deal with. And let me bring you here. And real quickly, let me explain something on these tables real quick, because I get this question a lot. People ask me, when do I know when to use this table to determine the temperature, or when we use the modifier, or when do we use this table, which is 310.15b12. Okay, so you'll see this table here is based on 40 degrees C. And this table is based on this one right here, if I can get you there. Let me... Right, this one's based on 30 degrees. So for any normal application that me and you will use, if we're using the ampacities in 310.16 and even 310.17 for free air, we're going to be stuck at the 30. So we're going to be using this table, okay? This one is only when we're dealing with a table for ampacity that is dealing with the 40 degrees C baseline, okay? So I can show you that by taking you up here and take you to the this thing here. Okay, so C310.16, that's the one we normally use, right? You see here it says the wiring is based on the 30 degrees C, 86 degrees Fahrenheit. That's what this table is based on. So that's why if you're doing a correction to the ambient, that is why you want to be in B11, because that is the table that's based on the 30 degrees C in any deviation from that, right? But I also will show you 17 is the same way, okay? That one is based on 30 degree 86 ambient temperatures. But when you get down into 18, you'll see that this one is based on 40. If you happen to use 310.19, you'll see this one is based on 40, okay? And these are other unique types of insulations. See, the temperatures are higher in these, okay? Unique applications. Here, 310.20, you see it's based on the 40. Those are the ones you're going to use 310.15b12. For you and me, we're going to be using 310.15b11 to apply our correction factors, okay? Oh, another thing that I'll add since we're here, and I'm already over as usual, okay? that. Another thing that I'll add since we're here is, let me go down here real quick. Let's get it to right here. Okay. Another thing I want to add is that when you're using this table right here to apply your ambient correction, the choice of which column to use is based on, to get your multiplier, it's based on your insulation's rating. So if we were doing an adjustment of correction and we were using just THWN, and we go over here to find the modifier, since that insulation is only rated 75, we would pull from this column. It's based on the insulation rating of the conductor. If it's a THHN and we're doing it and we're finding the multiplier, we're going to come over here to the 90, okay? That type of thing. So just keep that in mind. That's what you do when it comes to this table. This table is based on the multiplier, is based on the rating of the conductor itself, okay? All right, let me get back to the lesson here, okay? So the higher heat, 310.18, 310.19, it's different conductor use, different applications, okay? They're not the normal every day, and you'll know it. If you're working with 310.18 or 19, you'll know it because it's not your normal ampacities, okay, that you're going to be working with, okay? If you notice, 310.18 is talking about conductors that are rated for 150 degrees C. Those are unique installations where you might have something that's being run to an application where the engineer needs to have, there's going to be a much higher ambient temperature, there's going to be a much higher use group, and it may be for a fire resistance type of cable or conductor, and those conductors are used inside of it, and they may call for it. Your everyday building wire is never going to have that type of rating, that type of thing, okay? All right, so, and the next thing that we have to remember is when we have more than 3 current carrying conductors, okay? So that one is the, we're going to be looking at 310.15 C, and I'll go there real quick. And let's see, so here's C, more than 3 current carrying conductors. So this one is interesting, and I'll do a little bit of a little mini lesson on here because there's a lot of confusion with this. But first of all, just see the table. So here's the table, okay? So this is your adjustment factors when you have more than 3 current carrying conductors, okay? So if you have 4 to 6, then it's going to be an 80% modifier. If you have 7 to 9, it's going to be a 70% modifier, and so forth. Once you get down to 10 to 20 current carrying conductors, then it's a 50%, and it's going to screw you. If it's a 12 gauge and you're putting in 10 current carrying conductors, let's say, in a raceway, and a 12 gauge is good for 30, but you have to reduce it to 50%. So now you have a conductor that was rated for 30, under 90, right? That now has an effective ampacity of half of that. So it's now good for 15, but it was a 12 gauge, and maybe I have a circuit that requires a 20 amp circuit. Well, if the conductor now has an ampacity of 15 amps, then I have to protect it at 15 amps. Is that going to meet the rule for a circuit that may require it to be 20 amps? No, because now it's only good for 15 amps, and I have to protect that conductor at its what? At its ampacity. It's only good for 15 amps now. So in that scenario, I'm protecting it at 15 amps. So you have to be extremely careful in how you apply these adjustment and corrections because, again, even though our insulation is very resilient, it's not going to take you long to screw up and put more current through a conductor than it's designed to handle because of these conditions of use. And so you have to be very careful of those type of things, okay? All right, and of course, other things that we have to be aware of, and we're doing all this ampacities and using 310.16, we also have to be aware of this, what's called small conductor protection rule, 240.4D, okay? But basically, this is going to say if I have conductors of certain sizes, then I have to protect them, all right, at this certain value. So let's go look at 240.4D. And let's see what it says. These are considered the small conductor protection rules that we have to be aware of. All right, so 240.4, protection of conductors. Right here, here's the protection of conductors down here. And here's what you've heard me talk about many times. certain things like when you have overcurrent devices, 800 amps or less, and you meet all these conditions, and a conductor's ampacity doesn't correspond with an standard overcurrent device, and you're able to go to the next standard size. As long as you're not exceeding 800, these are the rules. And if you meet all these caveats, then you can do that. Okay. And then, of course, you get down here. If it is over 800 amps, then you want to make sure the ampacity conductors are equal to or greater than the overcurrent device that you're terminating into. Okay. Very common one right here when you're over 800. The small conductor rules. So this is a general rule. Okay. It says that unless specifically permitted in 240.4E or G, and we'll look at that in a second, this is general rules. It says the overcurrent protection shall not exceed that required by 240.4 D1 through D8 after any correction factors for ambient temperature or a number of conductors have been applied. Okay, so remember that example where I told you 12 gauge is good for 30? Okay, under the 90-degree column for purposes. But if I adjusted it down, and let's say it was 21 amps after I adjusted it, wasn't more than 9 current conductors. So I used a 70% and I adjusted it down and it was now 21 amps, okay? Because we know that 30 times, let's see here, is it 80 or 70? So 30 times 0.70, okay, is 21 amps. Right, Mr. Casio, right? So let me come back to me real quick. So Mr. Casio says it is 21 amps. So that is after adjustment and corrections. So I know that I have a conductor that's good for 21 amps now. But it says that I can't exceed the small conductor rules generally after adjustment and corrections. So what we have is that 12 gauge. So it was good for 30 under the 90. Okay, I adjusted it and I corrected it. It's now good for 21 amps. That's the new ampacity. Okay, but I can't use it at that 21 because the protection rules tell me in 240.4D for small conductors, what is it telling me? It's telling me that if I go down to this 12, and we'll just assume copper, unless stated otherwise, we'll go down and you'll see that right here, that 12 copper has to be protected at 20 amps. So that is the small conductor rule, okay? And that's how we follow those different types of rules, all right? Now, when we talk about what it said right here, unless specifically permitted in 240.4E or G, you have some applications where you have some tap conductors applications, and these have their own specific rules, which will allow you, for example, to have a conductor that is smaller that will be still protected by an overcurrent device where it may appear that, wait a minute, it's not protecting it. The conductor's ampacity is actually less, and you're protecting it with a greater overcurrent device. Under these specific rules, and you have to follow these rules specifically, that is acceptable, okay? But that is under limited conditions, and it's going to be limited length of conductors and things like that. And it's like, look, we're going to limit the load anyway, so we know that the conductor's okay, the insulation, everything's going to be okay. But the other one that you guys probably use every day of the week and you don't think about is this one, G. Now, G allows you to say, you know what, those general rules where a 12 gauge has to be protected at 20 amps, that's a small conductor rule. Well, I'll say screw that if you're dealing with motors, if you're dealing with HVAC equipment, if you're dealing with any of them that are down here that fall under the article that's referenced right here. So in our case, the one we see the most is here for air conditioning equipment, okay, here, but also motors right down here. You see where it talks about the motors for those conductors, falls under Article 430, Part 2, Part 3, Part 4, Part 5. That is where you might see a nameplate, for example, that has on a, let's just take an outdoor air conditioning unit. It might say maximum overcurrent protection, 40 amps, minimum circuit ampacity, 20 amps. And it might be, you're like, okay, well, I can use a 12 gauge and I'm terminating on a 40 amp overcurrent device. That's okay. Why? Because the running amps are going to be well within the conductor's ampacity that the conductor currently has, but we're going to allow the amps to surge for a short amount of time over the rating of the conductor, knowing that it's not going to be long enough that once the motor starts running or the air conditioning compressor starts running, it's going to allow it to drop back down. So we're able to follow the nameplate. Well, that means that we're deviating from what the code rule says, right? Because the code says that I have to protect the conductor at its ampacity. And those small conductor rules tell us that a 12 gets protected with a 20. A 14 gets protected, a 14 gauge gets protected with a 15. But we're able to deviate from this in some of those unique situations, like air conditioning units, like motors, okay? Again, motor. When we're sizing the motor's short circuit and ground fault protection, we may do it up to 250%. It's much greater than what we did the conductor's ampacity at 125%, let's say, for a continuous duty motor. How can we do this? Well, we do this because, one, the code allows it, and two, the dynamics that are involved in it. Remember that we have overloads that are designed to protect these conductors as well, and we have short circuit ground fault so that the motors can have that inrush, that starting, and all of that's going to work out. And so it's already been figured out. Okay, so you don't have to overthink it. But that is why we would use G to deviate from the small conductor rules, for small conductor protection rules. Okay. All right. So let's go back here to the lesson. I'm already over. I get it. Okay. So 310.14a tells us that no conductor shall be used in such a manner that it operates, it exceeds its designated temperature or the temperature rating of the conductor. So we can't operate it. So that's why we're doing all these adjustment and corrections in order to find out what the ampacity is now for this conductor based on a condition of use. Okay. Again, 310.15c1, that's where we get our correction for the, and this says 310.15 provides corrections for the ambient temperature. That is incorrect. That is for the number of current carrying conductors. Okay. So this is an example of rooftop, right? So again, you might have an overall ambient temperature up here that you have to take into consideration, right? And we know that it may exceed the 86 degrees Fahrenheit, 30 degrees Celsius up here on a rooftop. It's going to be hot, all right? And you installed this raceway on the roof. Well, hopefully you kept it above 3/4 of an inch. But if you did not, and you made a mistake, or you installed it on the roof, then from here to here, I might want to change this to XHHW, because XHHW-2 means that I can ignore the adder. I still got to take into consideration the ambient, which you normally would anyway, but I don't have to worry about that additional adder that would screw me over, and it would reduce my ampacity. So this conductor to here, maybe this is a box that allowed you splice in it, let's say. So let's say you ran up here, and this is inside of the building, all right, and you didn't have an issue for an ambient temperature issue. But the moment you got here, it changed, okay? So you could run into an issue on this part of your install that you didn't run into on this part of the install, okay? You got to be aware of that type of thing in your installation, okay? Let's see here. So this is an example where I can promise you that there's a good probability, not only for raceway fill, but there's a good probability that the individual did not take anything into consideration when it comes to number of current carrying conductors that are inside of this raceway. I can promise you that. All right, so if the higher ambient temperature is, and you have more than 3 current carrying conductors installed in the same raceway, then you may have to apply both an adjustment and a correction. You may have a case where you only apply one or the other, right? So in service conductors coming in from the outside, whether you do it or not, you probably are never going to have to apply an adjustment because you're probably never going to have more than 3 current carrying conductors. But you may have to apply an ambient temperature, and maybe your inspector calls you out on it, or maybe they don't know how to do it either, and maybe they just don't care, and that type of thing, and it's not. But it's just things that you need to think about. We already covered the adder part of it. Now, there is a little known, it has saved a many of the butt of electricians, okay? Saved many electricians, and it is the exception under 310.14a2. Now, you can't use this exception for non-metallic sheath cable, so don't even try to use it. But it is very common to use this in other types of cable assemblies unless it tells you can't within that specific code section. But this is something that's utilized all the time in raceways when engineers or design professionals screw up, or you have a small amount of conductor that may be running through a portion where it's maybe insulated and you've got to apply some kind of modifier because it's running through thermal insulation, or it's in a location that has a high ambient temperature and it's only a small portion of it. Like say I'm running a raceway in a commercial building and I'm going through a corner of a boiler room. So maybe everywhere else it's 86 degrees Fahrenheit, 30 degrees Celsius, but that portion that I run through the boiler room, heaven forbid, a design professional looks at that and says, whoa, Mr. Abernathy, you've got about 8 feet of this raceway that's running through this boiler room. And this boiler room, Mr. Abernathy, gets really hot. So the ambient temperature in this boiler room is going to change the ampacity of that portion of the run. And you're like, oh my God. So if it lowers the ampacity there, then it's going to affect the entire run. Because if my run that's not in that boiler room was good for 20 amps, but now that portion in the boiler room is going to drop my ampacity down to 15 amps, I'm screwed because it's going to screw up the entire run. Oh, what a nightmare that could be. Well, good luck to most of us as we do have, and again, it only applies unless somewhere else in the code says it doesn't apply. And for example, 334.80 for non-metallic sheath cable flat out tells you can't use this exception. Okay, so don't even try to use it for non-metallic sheath cable. But where you can use it, use it. And I'm going to show you what that looks like because it is an important rule that you need to be aware of, and it may save your butt one day. All right, so let's go look at 310.14 real quickly. And we're going to go to 310.14 right here. And I'm going to go down to 310.14. There we go, right there. Okay, so here is right here. So this right here is ampacities of conductors rated 0 to 2000 volts, all of which is still low voltage, by the way, if you didn't know that. So here's what it says. Where more than one ampacity applies for a given circuit length, the lower value shall be used. Okay, think about what I just said. If you're the electrician and I run a 100-foot run and 10 feet of that 100-foot run goes through a boiler room and my ampacity of my conductors were good everywhere else except for that portion that runs through the boiler room. Now you've got an issue, okay? So I have a higher ampacity outside of the boiler room for that conductor than I do now in the boiler room. And you say, why is that? Because the heat causes a reduction of amount of current that a conductor can carry because it moves it closer to the volatile point of the insulation. Okay? If the conductor has already got current running through it, it's generating heat. Now you throw this ambient heat around it, it's going to increase its temperature in that raceway and around it up to where it could exceed the insulation's rating of 90 degrees. What happens if it goes beyond 90? Well, the insulation on that conductor could start to break down. So how do we compensate for that? We have to lower the ampacity in order to keep that little buffer zone from getting to the 90 degree from the ambient temperatures. So, and obviously the current that's in the conductors, right? So that sucks because now I might have a conductor for just 10 feet that's only good for 15 amps, where everywhere else it would be good for 20 amps. And that's a 20 amp circuit. So that's going to screw me. And since the code said that I have to use the lower value for the entire run, so now that 20 amp circuit is dropped down to a 15 amp. But I needed 20 amps for that load. Can you see where that would screw you? Okay, looking at the exception. Here's what the exception says right here. It says, where different ampacities apply, and again, we had two portions of the run. The ampacity is different in the area where it has the higher ambient temperature than it is in the area which has the lower ambient temperature. That's what it's talking about. Two different ampacities in two different locations, okay? It says, where the different ampacities apply to portions of the circuit, It says the higher ampacity, okay, shall be permitted to be used. That's the portion that's not running through the boiler room. Shall be permitted to be used if the total portion of the circuit with that lower ampacity, and that is the portion that is running through the boiler room, does not exceed the lesser of 10 feet or 10% of the total circuit. Okay, so it's got to be the lesser of the two. Okay, so if it is a 100-foot run and 10 feet is going through the actual area that's got the, so in our case, 10% of a 100-foot run is 10 feet and 10 feet. So they're identical. So I get to ignore that 10-foot section and forget that the ampacity is going to be lower there. Why is that? Why can we do that? Well, that's because the conductor itself acts as a wicking mechanism. It pulls the heat away onto the conductor. It's a beautiful thing. I like to say our wires are designed to help everybody play nicer. Breaker manufacturers, lug manufacturers. If it wasn't for our wire acting like a heat sink, it allows the dissipation and pulling of the heat away, plus convection in a sense that we have a cooler area near an elevated ambient area. It's going to allow for the pooling or pulling of heat to convect out. So at the end of the day, it just works, and we're allowed to do that. Okay. Now, the problem is if that room was 11 feet and our run was 100 feet, we'd be screwed. We would have to reduce it down. And what would we have to do? We'd have to change the ampacities. I mean, we'd have to change the conductor size, okay? So one question that somebody put in here, I'm glad y'all asking questions because I thought y'all were asleep for a second. It says, Vanman says, could you put a junction box before the boiler room and upsize the wire going through the boiler room? You could do that. That's another question. Hey, that's a funny thing too. I had a conversation, again, since I'm over anyway, what the hell, okay? Coffee hours, plural, as Adam likes to say. Yesterday, I was asked a question where a engineer failed a guy because he ran a circuit and the drawings called for it to be 300 kc mil aluminum, but there was already a raceway in place that had 500 kc mil copper. And all he did was go to a junction box, use the proper terminating devices that allow copper and aluminum, and he switched over so he could use the 500 kc mil up these 9 stories. And then when he got to the top, he changed back over to 300 aluminum, used the proper lugs, and the engineer called him out and said that that is considered a feeder tap and it wasn't protected at its tap, and he called it a violation of the feeder tap rules. When I looked at that, I shook my head, because the engineer is the one that designed it in the first place. Why does it matter whether or not I use 300 aluminum or I happen to use a raceway that was there that already had 500 kc mil coppers in there? The 500 kc mil copper is good for 380 amps. There's no problem there. That is nothing more than a splice. Hell, we do this all the time when we do voltage drop. We increase the size, that type of thing. So absolutely, you could increase the size of the conductor. Just be aware that if you're doing it and you're increasing the size, that it could impact the size necessary for the equipment grounding conductor. Okay, so just keep that in consideration. If you increase the size of the circuit conductors for any reason, okay, except for if you're doing it for an adjustment or correction purposes, then you get to ignore that application. Okay, so we could argue that's what we're doing it for. So again, can be that argument there. But could you change it over? Yes, you could do that, and it might get you out of that situation. Absolutely. Okay. The other question I get from people is, can I go up to larger size conductors? Then nothing says I can't. If a conductor that I got can handle 20 amps, but I want to use a conductor that can handle 30 amps, that's perfectly fine. Just remember when you get back, let's say you're doing that down at the panel, like for a voltage drop, it doesn't require you to mark this or put a label. I would like it, and that's something that I'm going to introduce for the 2029, because I am actually going to introduce some changes for voltage drop. I'm going to put in a requirement that you tag it. And the reason for that is because I don't want somebody coming back later and seeing that larger conductor in the breaker and think that I can just change that breaker and go with a greater ampacity breaker because of the size of the conductor, because I have no idea what's on the other end. So I might have been just doing it for voltage drop. Okay, so a lot of variables there that we could talk about, but at the end of the day, sure, that could be, if you want to do that, you can do that scenario. But take advantage of this exception anytime you're dealing with that. And where's another good one that comes in? Let me show you a couple places where this isn't permitted real quick, just so you guys can follow along, okay? Just to show you. So, because people ask, so 334.80, I just want to show you right here. You see down here, see right here where it says this right here? 310.14a2, exceptions shall not apply, so you can't use it there. And you see down here where this is in yellow, this was my code change because I said to everybody, I said, dude, if I can't use it here, then I damn well better not be able to use it here. So this was my proposal. Sorry, guys. But again, I'm all about protecting our products. So you can't use it here either. All right, so that's an example there. But let's go see 338. Let's see what it says for SE cable. And let's go look here. And let's see here. If I go to 338, let's go down here and let's see what we got here. All right, so the use, okay, so temperature, again, this is telling us that we use 334 or excluding 334. Okay, so interior installations, yada, yada, yada. And here's the ampacities. And again, I don't see anything here that says, it says that installation-wise, I use part 2. So basically, I treat SE cable just like an NM cable. So I follow all of the installation rules in 334. I didn't know if you knew that, but you do. Okay, and that just means we didn't have to go into all this extra. You know, we don't have to cut and paste stuff from NM cable. We can just send you there, right? Then making this article bigger than it needs to be. That's a common practice in the code. But here we have where you have 2 or more. This look familiar? Where you have 2 or more SE cables containing 2 or more current carrying conductors, and each cable installed in contact with thermal insulation, caulk, or sealing. Okay, and you notice it says in contact with. Okay, not through it. So as long as it's touching it, then you have to do what? As long as it's touching it without maintaining space in between the cables, the ampacity of each conductor shall be adjusted in accordance with 310.15c1. We saw that earlier. But there's nothing in here that says I cannot use 310.14a2. And that is how you get around where you have SE cable and it goes through a wall that has got thermal insulation in it. And you have some inspectors say, oh, wait a minute, you got to have to adjust it right there because you have that. No, usually it's a small amount anyway. But again, that's why we had the rule 10 foot or 10%, because 10% of 10 feet is 1 foot. Okay, but even if it's smaller than that, then it gets down to be even smaller percentages. So it just works out. So again, it allows you to just ignore that contact with thermal insulation, that type of thing. Okay, so then you also see the rules down here as well. Here's your exterior applications for SE cable, and again, tells you to follow all these rules as well. So just kind of all that good stuff. Okay, so this is another example, but there's also others. So let's say here, let's go. And talk about, let's just see real quick. Let's go look at MC cable. And let's see, 330. Just look at 330. Here was MC cable. And we'll go down and look at MC cable. And we'll look at ampacity. Drop it down here. And let's look at ampacities here. Tells us to follow all these rules. Ampacity, conductors. And let's see. There's your thermal insulation requirement that you have to worry about. The same. 310.14, but I don't see anything in here that tells me that I can't apply 310.14a to the exception. So these are important things for you to remember because it just may save your butt in the future. Okay. All right. Let's see here. We'll cover the rest of this. We've already talked about terminal limitations and all this stuff. I encourage you to go watch our derating demystified video. And if you're not familiar with that is, I'm going to take you real quick to show you how you would find that over on Fast Tracks Tube. In case you're get rid of this guy who drives me crazy. All right, so I'm going to take us over to Fast Tracks Tube really quickly, just so we can show this to you where you would find our derating demystified video. Okay, here we are. So go up here to the search bar. So go up here to the search bar, and I would just type D rating. Okay, I'm gonna type D rating in here, and here you see right here, D rating demystified. Here is part 2, and here is part 1. Okay, and we even have the older 2.0 version. So we have the more updated 3.0 version right here, based on the 2023 code. So basically, you just log in here and you click it, and if you have an account, you can watch this video right here. And we'll talk about everything that has to do with adjustment and corrections. And that is a video that's available over on Fast Tracks Tube. And you saw how I just did a search and found it. Okay. Also, while I'm here, if you want to watch previous episodes of Coffee Hour, all you got to do is go over here to the series, click all series right here. And you'll see here's the Coffee Hour link. That'll give you all the episodes. Here's some of our Wednesday night recorded sessions. You can sit in like a fly on the wall and hear us discuss calculations. We have a bunch of them in there as well. And then here's that swimming pool and spa series. This is an awesome series right here. You see all the videos that are in this series. If you want to learn about pools, swimming pools, spas, hot tubs, all that kind of good stuff, this is based on the 2020 code. We will be updating it to the 2023, but this is a really good series. So that is available for you over on Fast Tracks Tube. And if you really are asking about calculations, just do this. Calculations. Type that up in the search bar. And if you type that, you'll come down here and you will get to see all types of calculations down here. Motor calculations, everything here is multi-outlet assemblies. Here's that 8-hour webinar that goes over all different calculations. Typically, this thing was $495 when we did it. You can get it as part of your Fast Tracks Tube, okay? All right, so with that said, I am going to do some spinning, and I'm going to have to do fast spinning because I am over. It's no longer coffee hour anymore. It's just turned into a beast of its own, and I guess because I'm long-winded and I can't help it. I am what I am, okay? Can't help it. All right, so let's do this, and let's do some spinning, and let's giving away some stuff here. Y'all ready? Let's go. You're in on the software. And I'm already going to miss my lunch today. I have ran over, so I'm skipping lunch today. So you're in the drawing for that estimating software. All right, good deal. Let's start this again. Let's go. You're either drawing for the mini knife. Sweet. I used my knife yesterday. I had to open up some packages and boom, my little mini knife was right there, baby. Love it. All right, let's do it again. Let's get some other ones in here. Let's go. Rapid drawings, folks. Rapid drawings. For you that are still here, for you that have left, sorry. Hashtag win. Get you in on the spin. Oh, beatbox. Oh, God. I'll say that to the end. Maybe most people will be gone by the time I beatbox. All right. Marlon, or is it Marion? I can't tell. I think it's Marlon. Anyway. All right, Lewis. Senior. Let's see what you got. Fast Tracks Tube. If you already have it, I will spin it again. I see my name. It passed it up. All right. So if you already have that, hey, what's up, Swartzy? I didn't see Swartzy in the room. Swartzy. Welcome, Swartz. Always love having the Swartz here. All right. Let's do this again. Hit the wrong button. Uh-oh, this thing is acting like the Matrix. messed your name up again. All right, Milton Toast. You are in the estimating course. You get a drawing for the estimating course. That's an awesome course, $500 value. And you're in on that. That's great. I have not taken that one, and I want to take that one because, again, it's going to be Steve Griffin, who is the creator of the Best Bid Hybrid Estimating, is a wealth of knowledge when it comes to things like this. So I can't wait to do that one myself. So that is awesome. All right, let's spin again. Let's go. Tino said, "What's up? Why are you skipping me, Paul? It's rigged. It's rigged." Yeah, I'm gonna think it's rigged when Marlon's got it twice today. All right. Well, I don't control the spin. It just does what it does. And Marlon, it says Fast Tracks 2, but you already just won that. So I'm going to spin it again for you. We're going to see what you get because you've already got that in this scenario. So we're going to spin it. We're going to do one more after this, and I'm going to cut you guys loose. And tomorrow we'll pick up where we left off in conductors, and we'll talk a little bit more about conductors and get a little deeper. Look at that. It's still just spinning. Oh, that's for you, Marlon, you got that again, so we got to do it again. What the hell is going on here? What is going on? All right, Marlon, we're still spinning it again here. We got to see what we get. All right, we're in the drawing for 12 months. I know, I'm just teasing you. You're in the drawing for Trade Hog, which Jeff just did an update on yesterday, so it's even smarter today. So you've got that. So you're in the Trade Hog drawing. That's a 12-month basic program drawing. So you're in that drawing, okay? We don't do Wednesday nights anymore. We haven't done Wednesday nights for 8 months, 9 months, 10 months. We don't do Wednesday nights anymore. In our course, you have what's called Fast Tracks Interact you use now. We've stopped doing Wednesday nights because you get me now 5 days a week on Mondays. We don't do Wednesdays anymore. All right, so let's spin again here. Let's get you. All right, last one here. That's old videos that talk about Wednesday night. I'm too lazy to go through and get rid of them. All right, Charles Bailey. All right, you get a Fast Tracks 2 subscription. Again, I've shown y'all before how you do that. You just basically go over to Fast Tracks 2. You just go up here under membership plan, click on membership plan, come down here, choose the free, and then fill out your username, first name, last name, and your email address, and choose your password. And then we will elevate you to the annual membership. Allow us 24 hours to be able to do that, and we will elevate you up. If it doesn't happen, then maybe we couldn't correspond your name with your username and the IP address. So then just reach out to us and let us know, and we'll get you all squared away. Okay. All right. Easy peasy. All right, guys, I got to run. I have a lot I have to take care of today. But again, shout out again to J&M Electric for having me up there yesterday, teaching that wiring cable class to you and giving you some code changes. I enjoyed it. Enjoyed meeting all your crew. And Jason, you're a great guy, and your wife is beautiful, and you're all doing great things for J&M Electric. So Richmond should be proud to have you as a contractor in that area. Okay, and we encourage your use of Prismium and Encore wire products in the future. We thank you for that patronage. All right, folks, join us tomorrow where we'll do a part 2. We'll pick up on more nuances when it comes to conductors and ampacities, and we'll do some calculations and we'll look at some things. That's tomorrow's episode. Not tomorrow's episode. That'll be Monday. No, it won't be Monday's episode. I keep forgetting. I am going to be a recording Monday, Tuesday, and Wednesday. I'm going to be gone next week. God, I keep forgetting. Okay, so we're going to pick up this episode on Thursday of next week. but you're going to get recordings for Monday, Tuesday, and Wednesday of next week. So you get a little vacation from me unless you want to watch the replays. Okay. All right. Almost forgot again. All right. Till next time, folks, stay safe. God bless. And we'll catch you on a future coffee hour. Appreciate all of you. God bless.